isomorphous system and in layer type system, and after that we have completed the eutectic system. Then we are going to discuss about last type of the uh, phase diagrams, that is the partial eutectic system. Already we have discussed about what is the meaning of the partial eutectic system, or when we are going to get this partial type of eutectic system. I will repeat it again, and I will explain this diagram again. Now here, this partial eutectic system, when you are obtaining that, if suppose you are having, if you are having an alloy which consists of two metals, binary alloy means two elements will be there, and these two elements are completely soluble in each other in the liquid state, and partially soluble in each other in the solid state, then we are going to get, we will end up with the partial eutectic system. Some examples I have written here, that is silver and copper, then lead and tin, then tin and bismuth, then lead and Sb, that is antimony, then cadmium, zinc, aluminum, silicon. So number of examples are there. Now this is the general diagram for partial eutectic system. Then I will explain it. I have already explained this diagram in the previous lecture. Then I will repeat some part. Now in this diagram you can clearly see that this line, see the upper side, point C. First I will explain this. Point C is the melting point of element A, and point G is melting point of element B. Then the topmost line, that is just below that, where I have indicated the liquid by letter L, below that CEG, this line is liquidous line. Above this line, metals or alloys will be in the liquid state only. Then next line is CDEFG. I will repeat it again. Line CDEFG. It is the solidus line. Below this solidus line, all the metals and alloys will be in the solid state only. Then uh, this line, horizontal line, you can see that DEF. This line will indicate, this will be termed as the eutectic arm, or it is showing the temperature at which eutectic transformation is occurring. Eutectic transformation line, it is also known as eutectic transformation line. Then there is two curves are there, HD and KF. These two curves are there. These two curves will indicate the solubility of the element A in B and element B in A. Now, before going for explanation of these two lines, HD and KF, these are solvous lines. We should understand what is the meaning of alpha and what is the meaning of beta here. Here, alpha and beta are nothing but the solid solutions. Now, alpha is solid solution of element B in element A. Means element A will be parent metal here, and element B will be alloying element. So, whenever element A is parent metal and element B is the alloying element, then whichever solid solution formed, it will be termed as alpha, and beta is the solid solution of element A in B. Here A will be alloying element and B will be parent metal. So this alpha and beta are two solid solutions of element B in A and element A in B. Now these lines HD and KF, these are termed as solvous lines. These two lines will indicate, or you can see that points marked here, that H point will indicate the solubility of element B in element A at room temperature, and point D will indicate the solubility of element B in element A at eutectic temperature, and this is the maximum solubility of element B in the element A. In the same fashion, or in the similar way, the point K will indicate the solubility of element A in element B, and or this is the solubility at room temperature, and at higher temperature, that is at the eutectic temperature point, that is indicated by point F, this is the maximum solubility of element A in the element B. These two lines HD and KF, these are termed as the solvous lines. Now, for the better understanding, we will consider one practical example for explanation of this partial eutectic system. Here I have taken one practical example of by taking one alloy of silver and copper. Okay, same diagram here also. I will explain the points here. The point C in the diagram, you can see on the temperature line, point C is there. This point C is the melting point of silver, and point G at the right top corner, point G is the melting point of copper. It is indicating point G, indicating the temperature 1083 degrees Celsius, and point C is approximately 953 degrees Celsius. That is the melting point of the copper. Now, the line CEG, top line CEG is the liquidus line. Then line CDEFG, it is the solidus line. Then line HD and line KF. Same names I have given here also. Uh, Same names I have given here as the previous diagram. These two lines HD and KF, these are the solvus lines. Okay, I will repeat it again. Point C is the melting point of silver, then point G is the melting point of copper, then line CEG, it is the liquidus line. Above that line, all the metals or alloys will be in the liquid state. Then line CDEFG, it is the solidus line. Below that temperature, all the metals and alloys will be in the solid state only. Then this line HD and KF, it will be termed as solvus lines, and these solvus lines will indicate the solubility of copper in silver and solubility of silver in copper at room temperature and at higher temperatures, that is at the eutectic temperature point. So this will be the description for this diagram, or different lines or terms involved in it. And after this, you have to take the different alloys composition, and you have to explain during the cooling process of the different alloys what will happen, or what will be the actual microstructural changes there. Now, first you have to mark here by point E. Exactly at the center, you can see that point E indicating the composition 28.1. It will indicate the eutectic alloy. Okay, eutectic composition. This point E is indicating the eutectic temperature. Corresponding composition, that is 28.1, is the eutectic composition, and that alloy with Ag dash 28.1% copper, 28.1% copper, it will be uh, an eutectic alloy. Then towards the left hand side, one more alloy I have marked with composition 20% copper. It is an hypoeutectic alloy. In the same fashion, towards the right hand side, you can mark the same curve. I have not shown that curve in this diagram, but you can mark the same curve, that will be hypereutectic alloy. In the center region where line DEF is present, here eutectic transformation will occur. That's why the part which is on the left hand side, that will be divided, or you can take that alloys as a hypoeutectic alloys, and part towards right hand side of that point E, you can take it as a hypereutectic alloy. Then you can see the leftmost corner of the diagram and rightmost corner. There again, you have to consider two alloys. One I have shown here uh, after point D in the left hand corner, and here I have not shown that curve. After point F, you can consider one curve here, but in these two curves, there is no eutectic transformation is occurring. That's why it will be just, you have to consider the cooling of the alloy with by indicating that composition. Okay, now here I will explain the three alloys microstructural changes. That is, first one, starting from the left corner, you can see that 6% it's showing 6% copper, 20% copper, and 28.1% copper. Okay, first one will be it is simply cooling of an alloy having silver and 6% copper. And what will be the microstructural changes that we will see in the next slide. Then after that, the next will be, this is the for 20% copper, it is hypoeutectic alloy, and then eutectic alloy. In the same way, after that, towards the right hand side of that 28.1, that is point E, hypereutectic alloy will be there, and alloy having the another composition you can consider greater than 92.1% copper. That explanation will be there. But what will be the similarity here? Towards left hand side of that point E, whichever alloys are there, you have there will be solid solution alpha. Just you have to replace whenever you are explaining the right hand side curve, after that point E, just you have to replace the alpha by beta and beta by alpha in the microstructural changes. Remaining procedure will be same, or microstructural changes will be same. Just only that instead of alpha solid solution, you have to consider beta solid solution, and instead of beta solid solution, you have to consider alpha solid solution. Okay, then I will explain these three curves, and remaining two curves you can draw that by your own by replacing alpha by beta and beta by alpha. Now we will start with the first curve from the left hand side with 6% copper. You can see this in this slide. First, please draw this diagram. This is the schematic representation of changes in the microstructure during the solidification an of a alloy with silver and 6% copper. And here I have marked the three diagrams A, B, and C. You can write it. I will wait for 1 minute. Please complete this diagram. After completion of the diagram, please put that you have completed the diagram in the chat box. Uh, okay, now if you have drawn this microstructure, I will start explanation. Now I will go towards the actual diagram, and please refer the microstructure which you have drawn. Okay, now that is the left hand side alloy I am considering here, silver and 6% copper. Okay, now I am explaining what will exactly happen, or what will be the microstructural changes when we are cooling it from liquid state up to the room temperature. Now from point 1 to 2, it will be in the liquid state only, that is not shown in the microstructural changes diagram. You can draw it in for your reference. Only liquid will be there from point 1 to 2, or region 1 to 2. Only liquid will be there, as both the metals are completely soluble in each other. Then when temperature reaches just below point 2, now here element A will start separating out here. Element A in the form of alpha solid solution, as whenever it comes in the solid solution state, as the both the metals are partially soluble in each other, they will form the solid solution. And here, as element A will act as a parent metal because its quantity is more, then here solid solution formed will be alpha solid solution, means in the region 2 to 3. In the region 2 to 3, some amount of alpha, will be there, and some amount of liquid will be there. Okay, means some amount of solid and some amount of liquid will be there in the region 2 to 3. And whenever temperature is decreasing in this range 2 to 3, as temperature is falling, amount of alpha will goes on increasing, and amount of liquid will goes on decreasing, as liquid is transforming to the solid. And as these elements are partially soluble in each other, they will form the solid solution here. And here, as silver amount is more, it will form the alpha solid solution. Then alpha plus liquid will be there in this region 2 to 3. Some amount of solid and large amount of liquid will be there. Then when temperature reaches at point 3, whichever amount of liquid is there, all that liquid will get transformed to the alpha phase. Means in this region 3 to 4, only alpha will be there, only alpha solid solution will be there. And that you can see in the diagram A, first diagram which I have shown in this microstructure. That diagram A is indicating only there will be only alpha grains are there. All liquid is transformed to the alpha grains, or you can say that all liquid is transformed to the solid, and it contains alpha grains here. Now when temperature falls below point 4, now what will happen here below point 4, when temperature is decreasing, now from this alpha solid solution, in this alpha some amount element, means element silver and element coppers are there. Then from this element copper will come out in the form of beta solid solution. Okay, and this beta solid solution will come out in two ways, depending on the cooling rate at the room temperatures. The diagram B and C, these two diagrams are shown the microstructures at the room temperatures by using the different cooling rates. Diagram B will indicate the microstructure at room temperature when cooling rate is very slow. Diagram C will indicate the microstructures when cooling rate is very fast or very rapid. We are doing the cooling with the very fast rate. Now whenever we are doing the slow cooling, then what will happen, whichever beta solid solution is coming out from that alpha solid solution, it will get segregated, or it will get concentrated, or it will occupy the grain boundaries of that alpha. In that diagram B, we can clearly see that the beta grains are present on only on the boundaries. As the cooling rate is very slow, it will get or occupy the spaces on of the alpha grains grain boundaries. Okay, all the beta grains will occupy the grain boundary of the alpha grain, and the microstructure will be as shown in diagram B. Whenever you are using the slow cooling, then in the diagram C, whenever you are using the rapid cooling rate or doing the cooling with very fast rate, what will happen? That beta grains will precipitate out, means some dotted particles or powder shaped particles you can clearly see in the middle of that alpha grains. That particles are nothing but the beta grains. Okay, so these will be the microstructures. Then you can here clearly you will get one question, that why these beta grains are coming out from the alpha alpha grains, why there is not a microstructure like shown in the diagram A. Then what will happen, why this is happening, these beta grains are coming out whenever you are doing the cooling. Then what will happen, it will form, means that alloy will goes in the super saturated state, means that this silver, in the silver, copper will get dissolved in the more quantity than its limit. Then whenever it exceeds its limit, super saturated solution, solid solution will be formed. And due to formation of that super saturated solution, whenever that super saturated solution comes at the room temperature, that extra amount will come out from that alpha grains in the form of that beta solid solution. Okay, and depending on the cooling rate, either it will occupy the grain boundaries of the alpha grains, or it will precipitate within the alpha grains in the form of beta precipitates or beta particles. Whenever cooling rate is slow, beta grains will occupy the grain boundaries of the alpha grains, and whenever rapid cooling rate is used, it will occupy the internal space of that alpha grains. Okay, so this is the explanation for the microstructural changes. If you are having any query, please ask me here only, or you can put that in the chat box. If you are clear, I will move towards the next alloy for the microstructural changes. If you are having any query, please ask me or put that in the chat box. I will explain it. Or if the microstructural changes are clear for you, you can put that also. I will move towards the next slide then. Okay, whether this point is clear, can I move towards next slide? Please give me reply. Only one.
Yes, sir.
Sorry, I'm not able to hear your voice.
Yes, sir, you can proceed.
Okay. Please draw the microstructures which are present in this slide. I will wait for 2 minutes, complete the diagram, and after that I will give the explanation for these microstructural changes. After completion of diagram, put that in the chat box that you have completed the drawing. Then I will explain the actual microstructural changes. Okay, this is the diagram for changes in the microstructure during solidification of second alloy which we have considered, that is the silver containing 20% copper. This alloy you can consider as hypoeutectic alloy. Here eutectic transformation is occurring and its composition is less than the eutectic composition. That's why this alloy will be hypoeutectic alloy. Please draw the diagram. Okay, now I think you have completed the diagram. Okay, now I will explain you what exactly happens. Now just put that microstructure in front of you, and I will take the reference from the actual phase diagram and I will explain it. Here, this is the hypoeutectic alloy with composition. It is silver and 20% copper. Okay, hypoeutectic alloy, that center curve, center dotted vertical line. Now I will explain what exactly microstructural changes will be there during the cooling process. Now from point 1 to 2, alloy will be in the liquid state from 1 to 2, and as both the metals are completely soluble in each other, only one liquid will be there. You can see clearly observe it. Then when temperature falls below point 2, when temperature falls below point 2, that alpha will start separating out from the liquid. Okay, this alpha is nothing but the solid solution of element B in element A. Means element A will act as alloying element, and here element A is your silver. Silver will be parent metal, sorry, silver will be parent metal and copper will be alloying element. Now alpha is the solid solution of copper in silver. Copper will be alloying element and silver will be parent metal. That will be your alpha solid solution. Means in this region 2 to 3, alpha solid solution and liquid will be there. And this you can see in the first diagram, which you have drawn now on the left diagram, liquid and some dendritic structure I have shown there. That is the alpha, alpha solid solution, and this alpha will be termed as proeutectic alpha or free alpha or primary alpha. Why it is termed as proeutectic? Because this alpha is separated before eutectic transformation. Actual eutectic transformation will occur whenever the temperature will reach at that horizontal line, that is the DEF line. Whenever any alloy, when temperature during the cooling reaches at that point, eutectic transformation will occur. And whichever phases are separating before that transformation, that will be termed as the proeutectic phase. Here alpha is separating out from the liquid before that eutectic transformation. That's why that alpha will be termed as proeutectic alpha, free alpha, or primary alpha. Okay, in this region 2 to 3, alpha and liquid phase will be there. This alpha is the solid phase and the remaining will be liquid. uh, and as temperature is falling from point 2 to 3, as temperature is falling, amount of alpha will increase and amount of liquid will goes on decreasing. And when the temperature reaches exactly at point 3, exactly at point 3, this is the eutectic transformation temperature. Is whichever amount of liquid is present there, the total liquid will get transformed to the mixture of two solids, that is alpha plus beta. This mixture is termed as the eutectic mixture. Liquid is transforming to the two different solids, that will be termed as the eutectic transformation, that will happen at the point 3. And in the next region from point 3 to 4, that microstructural changes I will explain in the diagram here. Now I will repeat it again. From point 1 to 2, only liquid will be there. When temperature falls below point 2, alpha will start separating out, alpha will start separating out. And in region 2 to 3, the total microstructure will be alpha and liquid. This alpha will be termed as proeutectic phase, or you can, it is also termed as free alpha or primary alpha, because it is separating out before actual eutectic transformation. And when temperature reaches at point 3, whichever amount of liquid is there in diagram A, it will get transformed to the eutectic mixture of alpha and beta. Okay, alpha plus beta. And it will be shown by the whenever you are observing this under the microscope, you will be able to see some line like structure, vertical and horizontal morphology will be there. And that mixture will be termed as alpha plus beta, that is eutectic mixture. Now in the diagram C, whenever now you are below point 3 in this region 3 to 4, what will happen in this region 3 to 4? As temperature goes on decreasing from that alpha proeutectic alpha phase, that dissolved amount of the means you can say that dissolved amount of copper in the silver, it will exceed the limit. Dissolved amount of copper in silver will exceed the limit, and that copper will come out in the form of beta solid solution. And that is shown by the dotted form, and that is the beta phase. That is the beta phase or beta particles. Okay, why these beta particles are coming out from that alpha? Because it is become a super saturated solid solution. Super saturated means it is solubility is exceeding the limit. Here silver is your base metal and copper is the alloying element. When amount of copper means amount of alloying element is exceeding its limit, then it will come out, and it will come out in the form of solid solution. Solid solution, and that is solid solution is nothing but the beta solid solution, and it will come out as in the form of precipitates. Okay, depending on the cooling rate. Here whenever higher cooling rate or faster cooling rate is there, it will come out in the form of precipitations, like I have shown in this diagram C, means in the dotted form. And whenever cooling speed is very slow, This beta particles or beta solid solution will get segregated at the grain boundaries of that alpha particles. Okay, this is the difference. Here only I have shown one diagram that is showing the precipitation of the beta particles. This is for the rapid cooling rate, and whenever you are using the slow cooling rate, just you have to show that beta particles instead in the center of that alpha grains. You have to show that beta particles on the grain boundaries of that alpha grains. Okay, so this is the microstructural changes which are happening for the hypoeutectic alloy, which we have considered with 20% copper. These are the microstructural changes. If you are having any query related to this microstructural changes, you can ask me. If you are not having any query, you can also put that in the chat box. Please mention in the chat box whether this point is clear for you, so that I can move towards the next slide. Only few students are replying. What about other students? Whether this point is clear for you, please give me reply. Okay, then now we will move towards the uh, third alloy which we have considered in the initial diagram. Okay, just it is very simple. Only one transformation will directly occur here. Just draw the diagram. This is exactly eutectic alloy we have considered. That is the third alloy, means silver and copper, with silver about 71.9, and the remaining amount, that is 28.1%, will be copper. This is exactly eutectic alloy. You can refer. I will move towards the this diagram. You can refer that alloy with 28.1% copper, indicating the composition represented by that point E. Okay, this is the eutectic alloy. Now what exactly happens here? From 1 to point E, alloy will be in the liquid state only, and when temperature reaches at point exactly E, that is the eutectic transformation temperature, that total amount of liquid will get transformed to the mixture of two solids, that is alpha plus beta. Okay, it is shown, and you, depending on its appearance, you can distinguish which is the alpha phase and which is the beta phase. They will be having different morphologies, and depending on the microstructure, you can clearly identify it. Okay, in one, from region 1 to E, only liquid will be there. Sorry, from point 1 to E, only liquid will be there, and this liquid will get transformed to a mixture of alpha and beta. This is the eutectic transformation. You can draw this diagram and give the proper names for that. Please draw the diagram. I will wait for 1 minute, or it will take only few seconds to complete this diagram. Whichever amount of liquid is there, it will get transformed to the eutectic mixture of alpha and beta. Please draw the microstructure. Okay, now as you have completed this drawing, now I will come for the initial diagram here. Now here we have explained the microstructural changes for three curves, okay, which you can clearly see here. Now whenever questions will be asked in the exam, you have to again add two microstructural changes diagram, that is for hyper-eutectic alloy, means composition more than this 28.1, you can assume any composition, and you have to show just microstructural changes, okay, microstructural changes, and it will be very much similar to the hypoeutectic alloy. Okay, that is the center curve vertical line, center vertical line, that is 20% copper, that is for hypoeutectic. And for hypereutectic it is very much similar, just you have to replace the alpha solid solution by beta solid solution, and beta solid solution by alpha solid solution. Okay, in the similar way, to the right corner, as we have taken the one curve to the left corner of that page diagram, you can consider one alloy having the higher composition than 92.1% copper. You can mention any value above that, and you can consider the cooling of that alloy, and you can refer this first microstructure, and instead of alpha you have to use that beta solid solution, and wherever beta solid solution is there, you can replace it by alpha. Okay, these microstructures you can add, means in this partial eutectic system total 5 microstructural changes diagram will be there. Okay, whether this point is clear, please confirm me.
Yes, sir.
We will move towards the next point. Okay, now some other important transformations are there. How much time is with us? I'm not able to see.
It's 10:52.
8 minutes.
How much? 5 or 10 minutes?
8 minutes.
Okay. Okay, I will complete the two transformations here. Now, somewhat that slide got disturbed. That slide got disturbed. I will explain it. Just some important transformations which will be helpful for you in the next chapters, or and some next points that I will explain here. That is Eutectoid transformation. You can see on the your screen or on that slide. What is the Eutectoid transformation? What is the Peritectoid transformation? Now I will explain it first. The Eutectoid transformation, both these transformation, that is eutectoid and peritectoid, these are solid state transformation, only solids will be there. In the first, that is eutectoid transformation, one solid will decompose to form mixture of two solids. Okay, means here in the diagram you can see that solid A will decompose to form two solids, that is solid B and solid C. That will be eutectoid transformation. One solid will decompose and it will form mixture of two solids. Some examples I have mentioned here, that is iron and carbon alloy, and copper and tin alloy, copper and aluminium alloy, zinc and aluminium alloy, aluminium and um, manganese alloy. Like these different alloys are there, means one solid will decompose to form two different solids. That is eutectoid transformation. And what is peritectoid transformation? Two solids, two different solids will combine to form a third new solid during, and all these transformations are occurring at a constant temperature during the cooling process only. Whichever eutectoid transformation means, one solid will decompose at one particular constant temperature during the cooling process, and it will form two different solids, that is eutectoid transformation. And two solids will combine at a constant temperature, and it will form a third new solid, that is peritectoid transformation. And some examples I have marked here, that is nickel zinc, nickel molybdenum, copper tin, and iron Nb is the niobium element. So these are the eutectoid transformation and peritectoid transformation. uh, Please try to understand in eutectoid transformation. In that slide, that arrow is got somewhat disturbed. I will repeat it again. One solid, during the cooling process, one solid will decompose at a constant temperature to form two different solids. That is eutectoid transformation. And two solids will combine to form a third new solid during the cooling process at one particular constant temperature. That will be peritectoid transformation. Then after this, eutectic transformation and peritectic transformation is there. Eutectic transformation and peritectic transformation is there. Now, what is the eutectic? Already I have explained it during this eutectic system and partial eutectic system. One liquid will decompose at a particular constant temperature to give the mixture of two different solids during the cooling process. It is the eutectic transformation. From one liquid you will get two different solids having different morphologies. For example, you can say that Fe and carbon alloy, or you can say that lead and arsenic, thorium and titanium, bismuth and cadmium alloys. These are there. Then the peritectic transformation. What is peritectic transformation? Here peritectic transformation is one liquid will combine with the one solid and they will give rise to a third new solid. This is the peritectic transformation. During the cooling process at a particular constant temperature, one liquid will combine with one solid and they will form a new third solid. uh, Third solid, that is the peritectic transformation. Here some examples again I am mentioning here. uh, Iron carbon alloy, then copper zinc, aluminum titanium, platinum and silver. Okay, here again somewhat that arrow is disturbed. I will repeat it again. Eutectic transformation, one liquid will decompose at a constant temperature during cooling process and it forms two different solids. And in the peritectic transformation, one liquid will combine with one solid to form a new solid at a particular constant temperature during the cooling process. All these transformations will occur during the cooling process only. And last transformation or important transformation is monotectic transformation. In this monotectic transformation, here one liquid will be there, and during the cooling process at a particular temperature, that one liquid will decompose to form mixture of one liquid and one solid. That will be termed as monotectic transformation. For example, you can see here clearly copper lead, aluminum lead, zinc lead, then zinc bismuth. Some examples I have mentioned. Whenever these transformations are asked in the exam, if only one example you can write, it will be sufficient. Okay, this is the monotectic transformation. I will repeat it again. One liquid will decompose to produce mixture of one solid and one new liquid during the cooling process. This will be termed as monotectic transformation. And you can see some examples you have to write here: copper lead, aluminum lead, zinc lead and zinc bismuth. Just try to remember the name of the transformation, what exactly happening here in the eutectic transformation, then peritectic transformation, eutectoid transformation, and peritectoid transformation, and last one is the monotectic transformation. Okay, in this way we have completed some other transformations which are necessary or which will be helpful in the next part. And in the next lecture we will uh, start the next point, that is the iron carbide equilibrium diagram. We will learn that, or we will start that in the next lecture. If you are having any difficulty, you can ask me. Otherwise I will end this session. If you are having any difficulty, you can ask me, or if all points are clear, confirm that. I will end this session.
No doubt, sir.
Okay, Rajwal is there.
Yes, sir.
Yash Gadekar, are you there?
Yes, sir.
Okay. Then I will ask some. Praveen is there. Praveen Somdare.
Yes, sir.
Okay. All points are clear.
Yes, sir.
Okay. Okay. Then we will. I will end this session here. In next lecture, please don't miss that lecture. It is very important point. That is the iron carbide equilibrium diagram that we will start in the next lecture. So I will end this session, today's session here. In this lecture, we have studied the partial eutectic system and some different transformation terms which are very helpful for further study. Okay, thank you.